Morning, everyone. It's my pleasure to be here. I came from Basra University down south in Iraq. It's a long distance to come, but I'm glad I made it. I faced so many problems to come here. I mean, financially and others, you know, USA visa. I've been in the state 3 times before, and I faced some, I applied for another conference, and the visa was a bit delayed. So they considered asking me, "Are you still want to go to state?" I said, "Yes, I have another conference." So I came. I'm glad I made it. My name is Hadi Al Lami. I'm head of chemistry department at College of Science in Basra University. I am chemist. I am working with polymer and ceramics. My base is polymers. When I went to the UK, I said to people I met that time to supervise me, I said, I want to work with polymers and a new work. So when I return back to my country, I can continue. Because we found a lot of people at that time, they went to state or they went to UK and worked with very sophisticated instruments and techniques which are not available at our department. So they keep changing their specialty. Thank God I didn't do that. This is a part of PhD thesis. He is still working. So when I applied for this conference, I sent the result we had that time. And I kept continuing with him. So we got from the day I sent the abstract up to yesterday, we got another result. So I included, sorry for that, I included to make the full story of it. Sorry, this comes in here. So maybe it's different. Anyway. This is presentation outlines. We are going to talk about applications, scope of smart polymers, definition of CRB, controlled radical polymerization method, ROP, ring opening polymerization method, and the new techniques which called thio-click polymerization. The name is surprising because it's including a click. It's come from the computer. When you are working, you just click to get what you want exactly, to open this folder, to see this picture, to see this. So that means in this chemistry, you are working with a special group. So you work in that, you make the conditions, the circumstances of the reaction to go in this, exactly this position, not in the other position. So we did it, and we succeeded. Synthesis of nano multi-arms block copolymers, then characterization by microstructure studies. We did some, this is the news, we did some swelling, biodegradability, and drug delivery study. And then we did some thermal studies, and there's some inclusion. Smart polymers, all of us we know as smart material. That's why we are here. They are very clever material. It has, from my point of view, it has a special properties, so we can use it instead of other material, which is, they don't give you the same function, the same application, the same. So you have to be careful when you are preparing such a materials to be applied for different applications. These, some applications of smart polymers, exactly smart biopolymers. Smart polymers, there are different areas. We are going to concentrate on the drug delivery system because, in fact, my PhD, I did some work prepared on a group transfer polymerization method. It was patented here in UK by DuPont company. I prepared a polymers, novel polymers at that time, 1983 it was, and I used it as dispersant for ceramic processing and as a binder. This is the newest part I worked with that time. When I came back, I continue working in this, and I keep changing from area in the same field of polymers. For example, let's put it this way. We work in drug delivery. We are exploring some polymers. Of course, drug delivery, I mean, to use a polymers as a drug delivery system or another, it has to have a certain properties. The first one is about biocompatibility and toxicity. Because when you use it inside the body, it shouldn't have any toxicity. We have another PhD student started this year. In our department, we have a very good, clever lady, a PhD lady. She is a biotechnologist. So we made two joint projects. MSc, she graduated 2 years ago. And the other student, PhD student, we are going to work on gene delivery system, gene therapy, all of these things. These definitions of methods of polymerization, maybe most of you are not familiar with it, but I explained their names from their initials. This is different chemistry, different functional groups. The B from 4, this is the thiol-ene reaction. Thiol, all this goes with double bonds with others. So why we use this? Because we were planning to prepare a huge molecules. You will see it. This is the preparation techniques we use. Vacuum line, nitrogen line, cooling, normal temperature, I mean room temperature, or lab temperature, whatever. This is first polymer we prepared. We took pentyrethrotol, we polymerized it with lactide during ring opening polymerization. We got this polymers with 4 arms first. This will become our starting material because as far as we have the OH group at the end of the molecule, so you can, as a chemist, you can, we play it with it. We can join it with other molecules, we can substitute it with another molecules and carry on. I'm not going to concentrate on chemistry. This is what we prepared in the previous slide. We made the molecule bigger. It's also 4 arms, but it's a bigger molecule. And you can see this is with the blue material. It comes with a green material. This is the catalyst and all these things. When you precipitate the polymers, you get it sort of, not glassy, I mean it's viscous, nearly some of them is solid, but they are clear, okay? Because this color comes from the catalyst we used. We started to prepare thiolate pose. The pose is a big molecule, this one. This we bought it directly, we didn't prepare it. And then we worked it with this diol molecule end group. We started to get this. This is the morphology or the shape of the molecule, the product we got that time. This is preparing a thiolate pose. We reacted with N-hydroxyethyl acrylamide to prepare copolymer, this one. This is the huge molecule. We got it with multi-8 arms. It's 8 arms, so we call it a multi-arms. So we prepared 4 arms, 6 arms, 8 arms. A molecule with all these arms. It's a huge molecule. This is the characterization. This is the IR. I'm not going to take time in it. This is the NMR, proton NMR. This is carbon-13 NMR. So all the polymers we prepared exactly what we planned to at that time. And of course, I mean, we can measure the purity of the molecules, of the polymers, from the baseline of carbon-13. Although there is some in here and here, but is still very, very low. I mean, working with such a huge molecules, we're expecting some impurities, but as we are going to show to you, it didn't affect the properties, it didn't affect the molecular weight, which is very important. This is the thiolate boss, IR, this is the carbon-13. This is IR of thiolate boss with lactide. Why we are using lactide? Lactide is a biodegradable polymer, the most famous biodegradable polymer. They use lactide, lactic acid, lactic anhydride the most, okay? So we just changing the other monomers to get use of biodegradability of the lactide itself. It's not, I mean, we pretend we polymerize lactide for the first time. No, it's well known. It's well known. But the other molecules, the other monomers, they are the new applications on a new preparation of these molecules. We used 3 different types of modern polymerization. ATRB, atomic radical transfer polymerization, ring opening polymerization, and thio-click polymerization. The literature with ATRB, they say, I mean, let's say the polymer. The polymer has different molecular weights. 3 different types of molecular weights. If you need a good application, a smart polymer, the chains should be equal to each other. Should be equal to for different applications. Say for microwave, for communication, for laser applications, for. They should come from one side and go out from another side. If they, I mean, if some of them come, if there's some differentiation in polymer chain, so that means there will be a lot of noisy bits because they're different in wavelength, different in frequencies, so they will be each one translates each one. So the literature with ATRB said the dispersity, which is molecular weight, molecular weight divided by number of molecular weight, varies. Thiolate boss molecule. This structure or this microstructure of the multi-arms nano-block copolymers comes in this way. It's directly inside, I mean, it comes in as a closed molecules. So we can't get advantage of this to be used in a drug release system. We did swelling studies recently, I mean last week. The PhD student, he did it. He didn't send me these, the figures, just, he did biodegradability studies. He did biocompatibility studies. Biocompatibility studies, these copolymers, the way of this measuring this one, there's some control. We did this in vivo outside the body. We took blood from certain, I mean, students or our staff who are willing to give us a few millimeters of his or her blood, but we stick it to it. This is the control. We add the control and the blood, and 1, 2, 3 is different concentration of each polymers. So you see, we didn't have any precipitation. That means the blood cell didn't precipitate. So that means it's non-toxic. Why? Because the material, the starting material, one of the starting material, when we test it, the starting material, when it becomes a polymer, you see the precipitation here? So that means our polymers, this is the first indication for non-toxicity. This they call a cytotoxicity test. We did some experimental. We loaded these polymers by insulin, which is, this is what we're trying to do in here. You know, I mean, the diabetes peoples, even, which one of them, when it goes to injection insulin, after 1 year or 2 years, he got fed up. He got a lot of bloody holes in hand or in knees, near knees, or these things. We're trying to take the insulin orally. rather than by injection. We started, we didn't reach that much result, but it is encouraging. For example, this is one of the copolymers, multi-arms nano copolymers, loaded with insulin. We did some swelling, we did some biodegradable, we drug delivery. We ended by microsector, it appears a small amount, white spots. This is for insulin, for the remaining insulin. We compare this with the literature. This is from literature, this is our work, this is from the literature. So we can see it's nearly the same, but the size of insulin is much bigger than ours. That means our polymers release more insulin than the other, than what they said in the literature, which is, I mean, I consider it is a very, very encouraging result. We did some thermographic, I mean, we did thermographic before the biodegradability and all these things. We have a result. You know, it's nice to know some properties and thermal properties, our stability, thermal stability of your polymer, because you never know where will be storage, who will be going to use it, okay? Just to have an idea. This is the PL10, one of them. Of course, I mean, this number is 10. We prepared polymers, copolymers with different number of lactide polymers, 10, 25, 50, 100, okay? So different polymers we prepared having different chain of lactide. I should mention this before. This is smooth analytical. This is the temperature where, this is the temperature where the char contact started. What we call it T 50% from weight. It stands up to this temperature with 50% of its weight. So I mean, if we start with 1 gram, the remaining is half a gram at temperature, from room temperature up to 225. This is some calculated properties, thermal properties. You can see this one, the T50 is increasing with increasing the chain length of lactide, which is expected, this result. But we don't have the numbers. We don't have the numbers. This is for thiolate boss with lactide. This is the third polymer, the multi-arms, big multi-arms polymers. Here, we start to have first decomposition and second decomposition. That means we started to get more stable copolymers thermally. More stable copolymers thermally. What caused this one? You know, it's a big molecule under aggressive heat conditions, of course, under nitrogen atmosphere with heating rate is constant. But when you have an aggressive conditions, the more polymer molecule degrade thermally and started to reform again, because the atmosphere is there some acid, some alcohol, and some. So it started to react. So that means it started to protect themselves from heat. So that we got first decomposition at 206 and at nearly 290. And look at the T50, it's increased to up 356. It was about 200 something. So there a 100-degree stability difference, which is very, very good to consider. This is also all the, of course, the T50, weight 50, is increased than what we had before. The conclusions, combination of ROB with thio-click chemistry has been reached with success using ATRB. And I am proud to say that this is the first time in Iraq, or maybe in the region, to do ATRB and thio-click chemistry, honestly. All these tests, it has been characterization, it has been in Michigan University. My students came last year on some kind of collaboration between our ministry, higher education ministry, and they give 6 months for the PhD students and 3 months for MSc students, and it has been cut now due to the budget decreasing, you know, I mean, all the oils and these things, the prices. If you allow to me, I will show you some Basra, where I come from, in figures. Basra in some pictures. This is Basra on Google Map. This is the river Shatt al-Arab. This is Basra International Airport. This is University of Basra Presidency. This is our college. Of course, it's famous in date palms and date trees, all these things. This is one of the celebrations. I make it faster too. This is Lion of Babylon statues, which is the original one in Babel, but this is our students in polymer lab. This is the way to cut or to take some date palms selectively during its growing. This is the graduation ceremony. I mean, our students, they used to celebrate, as I mean, I think in the state or in England, a week or a month before their final exam. So always we invited to this. This is my colleagues. This is Shatt al-Arab rivers. Sorry. This is oil ports in El Fao. We're loading. This is some of our staff. This is, they call it Abu al-Khasib, which is on the two sides of the rivers, of Shatt al-Arab rivers. This is after the ceremony we give. This is marshes in 70s and 90s, and now it's been removed due to political thing. We had a conference last year. This is the receptionist of the people who comes to the conference. This is Basra Sheraton Hotel on the river bank of Shatt al-Arab. This is the oldest bank in Basra. This is in 50s from the last century. You see the old cards, and you can imagine it's black and white. This is marshes. This is where people in marshes live. It's in south of Iraq. This is Sheikh of Qabila, Sheikh Khaz'al, they call it Sheikh Khaz'al. It's been taken by last regime. This is the ladies from marshes, driving and cutting all this to be. This is where, you know, we have a big 2 rivers in Iraq. This is where they met in Gorne, north of Iraq, which is about 70 kilometers north of Iraq. This is, I mean, free farms for cows and all these things. I mean, I'm sure if you go there in this exactly the region, we can't find any trees anymore due to so many reasons. Fishing, the old way to fish by net. This is river when it comes toward the Gulf. This is the big port of oil port, Khor al-Umayya in Fao. This is where people fishing, the local people fishing. I mean, the river Shatt al-Arab divided Basra in 2 parts, major parts and the other parts. This shopping, this is trees. Of course, we are famous in camels, Arabic camels in the region. This is restaurants, floating restaurants in the Shatt al-Arab. It's a very nice place. You are invited, if you can make it, please. All these ships are near the port of Basra. This is one of the houses. This is thank you in so different language. I will say shukran, and you say it in your language. Thank you very much indeed. Thank you.